Okay, I'm just going to show you why, in fact, you learn to slide vectors. You learn to slide vectors and add vectors not so you can necessarily get an exact solution, because it's a lot easier just to do the matrix algebra or some of the other things, but it's a way for you to really quick get a general answer what your solution should look like. And so I have in front of you, I'm going to just demonstrate really rough some of the capabilities of scening and transitioning in SketchUp here. So I've done this by setting a style up in SketchUp. I'm just going to show though for those who are in styles. My style actually is set up so the color is by the material on the edges and over here, and I'm showing color by layer. So I've set up a style like that, and I've got three forces on here, which I won't necessarily keep track of so much. You have a pin joint on the left, which means a reaction of unknown direction, and a roller joint on the right, which means a reaction of known direction. So that's how you start. Remember, what you need to do is you need to, any number of things, you either use superposition or simplification, and when you're adding a bunch of the known vectors together, you're doing simplification. So how do you go about doing that? You pick two known vectors, in this case these two here, and you're looking for a point of concurrency. Now in this case, very often you want to ignore that third vector for now, but in this case we have a point of concurrency, right? Something like that right there for these two vectors. What do you do then? You slide those vectors, right? You slide them up to that point of concurrency, and then add them tip to tail, and you get a result. So this here, if I go back, that black line is the resultant of these two lines here. And if you visualize that, this one's going up there, and this one's coming back down there. And so that is your resultant. Now what do? Well, you get rid of these two, and you do it again with the next vector. In other words, you have this vector that's coming out here and this vector here. Once again, you pick its point of concurrency, you slide each of these to their point of concurrency, add them together, and you get something like this. This is this vector that they add up together. Let me go back and just visually let you check. In other words, this one was coming up and this one was going over, so you have a vector that looks something like this. But of course, where it's sliding is going to be based on this point of concurrency. So up, over, and you get something like that. You now have this solution in actually now three vectors. So this is one of them, another the resultant of all the applieds. You have the known direction here of the one through the pin joint, and you have a, then by knowledge of the fact, I'm going to get rid of this one here, by knowledge of the fact that you have these two concurrent and that the third force has to be concurrent, you now have the line of force for this reaction. So you know this is the direction of the pin joint. You can then more or less solve this by mathematics if you know the known directions, or by that basic graphic solution of you know this is the vector here, you're going to pick your direction home, and then you can get there by doing this. Traveling, hitting a control key to copy, traveling along this direction. So your reaction at A turns out to be this, and your reaction at B turns out to be that, because you know they all have to add up to be 0. And so that's the final piece of what you do on a simply supported beam to solve it graphically. So you more or less simplify, going through it one more time, you simplify the applied forces by daisy chaining. And then, once you're done, you take that resultant, take its line of force and the line of force of the known direction, come up with a point of concurrency, and that tells you the line of force for the other reaction, the pin joint, and then you can use your calculator or use sliding triangles to solve basically what becomes a concurrent force problem. So that's, I'm not going to call that a trip. That's how you're originally supposed to really learn to solve vectors. You do that in a lot of land navigation classes. So anyway, we'll print this out, talk about it, and then realize that probably it's going to be easier just to learn to use your calculators and some mathematics for some of you. But learn to come back to this. Thanks for listening.